Today I'm going to talk a bit about some convolutional architectures for image classification and image segmentation. And after the break, I'm going to introduce the Keras functional API and talk a bit about the second assignment. So today I'll try to keep the lectures shorter so that we have more time for questions, mostly I think about the assignment after these lectures. In this first lecture, I'm going to give you a sample of different architectures that have been used for image classification, and I'm also going to talk about image segmentation. We didn't see that yet, but I'm going to give two examples of two deep networks used for image segmentation and explain the problem here. The idea of this lecture is not to cover every possible solution because there are many different ways of creating these networks, but to give you some examples to illustrate some problems that were found and solved and the techniques used to solve them, and also to reinforce this basic idea that deep neural networks are very versatile. We can build different models very easily using these networks. So let's start with the problem of image classification. You already did some exercises with this, and using convolutional networks for image classification is the state of the art nowadays. It's what works best. And we can see here maybe the first real success in using convolutional neural networks for image classification, the AlexNet. And you can see the architecture here. I already showed this diagram on the first lecture, but we did not had the convolutional layers covered by then. So now we can look at this in a bit more detail. One thing that they had to do, this was in 2012, they had to split the network into two separate channels for most of the network because of memory limitations. So they used two graphics cards. And for example, in the first layer here with 96 kernels, they had to split 48 for each graphic card. And they had to keep doing that, so splitting into the two streams with different channels and then gathering everything together at the end on the final layer. But you can have an idea of what the kernels were used. This first convolutional layer with 48 kernels in two different cards, so a total of 96, but they were 11 by 11 kernels. So the receptive field in the image of these kernels was 11 pixels by 11 pixels. Then they had this 5 by 5, then 3 by 3. So you see as after pooling the resolution of the feature map, so the total size of the feature maps reduces, and then they also reduced the dimensions of the kernels as they were progressing along the network. The idea here was that this initial kernel of 11 by 11 was capturing a sufficiently large area of the image in order to identify relevant patterns, because if you only look at a few pixels, you probably will not find anything useful in the image, but if you look at a wider patch at a time, then you get more information. Of course, this led to a large number of parameters. This network had 60 million trainable parameters, and also a very large amount of memory necessary to keep all these feature maps. So remember that the parameters are determined by the size of the kernel, mostly 11 by 11. It means that you need 121 parameters for each input channel into this kernel. And then you also have the memory requirements to keep all these feature maps. So if we have here a feature map that has the same resolution as the image, which is 224 pixels square, then you need that memory for each of the feature maps, and if you have 96 of them, then you need to store that whole tensor, and if you are doing mini batch, you will have one for each example in a mini batch. So all of these things, the number of layers and the size of the mini batch will also influence how much memory you need to store all these tensors during training. So remember this when you are training convolutional neural networks, because if you are using more than the memory you have available, then things performance degrades quite a lot. For example, if you use more memory than you have available in the graphics card, then you need to keep transferring data from your RAM to the graphics card and back, and that will take some time. And if you take more memory than you have in RAM, then you start swapping and everything stops practically. So this is one concern when training these networks, how much memory we have and how much memory all these tensors take. One thing that you can do to control this is to reduce the batch size. That's an easy solution, because the smaller the mini batch size, the lower the memory requirements for all these tensors during training. So the idea here for this network, and it is the general approach for classifiers using convolutional layers, is that we have most of the network in convolutional layers that are extracting features. They are identifying the correct patterns. The pooling operation serves to make the detection less dependent on specific positions in the image. And then as we start converting the spatial resolution here in the original image into more filters, and these filters responding to more complex patterns, when we reach here the end, we can flatten everything out and pass on to dense layers, and these will do the classification. So the idea is that at this stage we already have data that is in some way structured, because we have the different filters responding to different features in the image, and now we pass on to dense layers that will look at those different features and compute the best way to classify them, to classify the examples using those features. So this is the general approach for classification. Use convolutional layers to extract the features, and then dense layers to classify. One problem with this network is the use of very large kernels. For example, this 11 by 11 kernel here, each kernel of these 96 will need 121 weights per input channel. Since the image is in color, you have 3 input channels, so that's 363 parameters for each of the 96 filters that are being used here. And this, when you use large kernels, for example here 5 by 5 and so on, you have many parameters here in the convolution layers. And this, on one hand, may be necessary because you want to look at larger fields, receptive fields for your neurons, so that you don't just look at patterns in very few pixels. But on the other hand, if you have too many parameters, then you start having problems with overfitting, and the performance in the classification worsens because of that. And you also make training harder. The larger the number of parameters, in general, the more difficult it is to optimize the loss function. So one thing that VGG16, a network that came 1 or 2 years later, tried to solve was this reliance on very large kernels. And the way they did this was by stacking smaller kernels. So you can see here the scheme of this architecture. We have here in gray convolution layers, in red max pool, and then we have here the dense layers and the soft max layers. So this was for ImageNet. There are 1000 categories. So the soft max layer has 1000 neurons. There are 3 dense layers here. This is that top part that does the classification. And here we have all the convolutional layers that are extracting the relevant features from the image. This is from the same data set, the ImageNet, so also 224 by 224 color images. This is the input. But you can see that we have here several convolutional layers stacked, and then max pool, and then we have 3 max pool and 3 max pool and so on. And the reason for this is that we can get effectively one kernel having a larger receptive field on the input by stacking with an intermediate layer of the same kind of convolution. So you see here, this kernel only has 3 positions in width, and the same thing for these ones. So these are all kernels of 3 in this dimension. But if we stack 2 of them, this one here is actually receiving input from all of the 5 values on the input layer. So the trick here is that if we stack smaller kernels, we can get the same effect as using one large kernel. And the reason why this is an advantage is that if you have, for example, a 5x5 kernel, you need 25 parameters per channel, because this is the size of the matrix of the weights for each input channel. Remember that this is for each input channel. So if we have here 64 channels here, so we have 64 feature maps on this block. This means that each kernel that is on this layer here will need to look at the receptive field 64 times, because it's aggregating the data from all of those channels. So this can be a large number of parameters when you have a large number of filters coming in from the previous layer. So if you're using 5x5, you need 25 parameters. If you use 11x11, you need 121 parameters for each input channel. But if you replace, for example, the 5x5 with a stack of 2 kernels of 3x3, so you're doing this thing but in 2 dimensions, then you only need 18 parameters, because each of these only takes 9 parameters per channel. And this is a significant reduction. When you go to larger sizes, the reduction is even more significant. So if an 11x11 kernel is replaced by a stack of 5 kernels of 3x3, then you go from 121 to 45 parameters per channel. So this in VGG, they use stacks of 2 or 3 convolutions using always kernels of 3x3. So this allowed them to create something that was equivalent to using larger kernels, but with fewer parameters, and this improved performance in the network. Another problem with training very deep networks is that if you imagine the input coming here, and then you have these operations with all these convolutions, so in this case you have 64 kernels generating this first set of feature maps, and then a further 64 here, then you're pulling, and then more kernels and so on, and all of these gray blocks are initialized at random. So it's easy to see that once you pass your input image into a set of 64 random kernels, then basically you get garbage coming out here, and the second set of kernels will not have anything useful to learn until the first one at least starts producing something that is minimally useful. And this will have to work through all the network during training. You need to start organizing the previous layers before the subsequent layers can learn anything useful, and this slows down learning significantly. And this is especially serious when you have very deep networks like these are. So ResNet tried to solve this problem, or mitigate this problem, using residual blocks. And the basic idea, we can see this in the simpler version, is that you have here convolutional layers. So this is a stack of 64 3x3 kernels, rectified linear unit activation, and then another stack. But you also have a skip connection here. So you're taking the input into this first layer, you're also copying it and adding it to the output of this second layer before applying the rectified linear unit. So this is something that may seem a bit strange, but what we're actually doing is, because the original input is added to the output of this block, we are making this block learn not the correct output, but the difference between the input and the correct output. That is called the residual. So the difference between some target and what you have is the residual, and this is what this block is learning. What are the values that, when added to the input, will create something that we need or that we want for the next step. And the reason why this is helpful is because even in the beginning, when all of these weights are at random, there is still some useful information moving on through the network via these skip connections, because we are copying the input into the output, even though it's being changed by those initial operations with the random weights. If the weights are very small, this change can start small, and so the network can learn more easily because all the layers are getting some useful information. In fact, ResNet created here also an additional innovation, was the use of these kernels of one by one. So you have kernels that are only looking at one pixel on the feature map. The usefulness of this is that if you pass a kernel of one by one dimension over the input, remember that the input is a stack of feature maps. So your kernel has one weight for each of the feature maps. And then it will produce a new feature map that is a linear combination, pixel-wise, for each pixel, of the previous feature maps that you are receiving as input. This means that if you have an input of, say, 256 feature maps, as in this example, and you pass them through a stack of 64 one by one kernels, then you output from here a feature map, a set of 64 feature maps that has the same dimension, but now you reduced from 256 to 64 by looking at the best linear combinations between them. So one by one kernels are a good way of compressing the large number of feature maps into fewer feature maps while preserving all the spatial information. So it's not mixing pixels one with the other, it's just mixing the feature maps in the same pixel. And this allows these blocks to simplify the computations here, because you start with 256 feature maps, you compress it to 64. Now these kernels will only have 64 channels as input and not 256. So this reduces the number of parameters you need on the 3x3 kernels. And then you create 256 feature maps from linear combinations of the previous one. So this was the idea, that the one by one convolution would only do linear combinations of the feature maps. But actually, the authors found that if they added rectified linear unit activations to these layers, so they are not only doing linear combination, but then a non-linear transformation, this even improved the result. So basically, these one by one convolutional layers are computing these linear combinations of the input feature maps, and then using a nonlinear transformation with a nonlinear activation to further transform that input. And this is used to control the number of feature maps that you have at each step in these blocks. So using these techniques, ResNet managed to create, be able to train a much deeper network because of these skip connections, and using these techniques of changing the number of feature maps, it's easier to adjust the number of parameters you need at these convolution layers, and so adjust the power of the network in order to improve training, avoid overfitting, and so on. Now, one network that came later, GoogleNet, was trying to solve a problem with this approach of building larger and larger networks. So it was clear by this time, so this was in 2015, it was clear by this time that if you need more powerful models to solve harder problems, then you can increase the network, the number of weights, the number of layers, and so on. The problem is that we are doing all these operations with dense matrices. So everything here, all these feature maps, the kernels, and so on, we are doing all those matrix multiplications, all those operations with the matrices that are fully filled with all the values. But we know that only some combinations of connections are necessary. So ideally, we would use sparse connections, something a bit like our brains. Our brains are not fully connected, all the neurons to all the neurons. Each neuron is connected to only a very small subset, and so on. We can see this also in neural networks when we use dropout. Dropout works precisely because we don't need everything at once for the network to work. Only a subset is already enough to make things work. However, it's hard to implement sparse matrices and so on in the hardware, in the GPU and CPU, in all these operations, because you have a lot of overhead. If you're dealing, for instance, with sparse matrices, you need to keep track of which coordinates have values and all the rest are zeros, and so on. So part of the motivation was trying to create blocks that use the regular operations we are using in these neural networks, but try to approximate what would be ideally a large but sparse network that would solve problems without having too many parameters. So the idea here was to design these blocks that worked in parallel at different scales of the input feature maps and images, but avoiding too many parameters. And this was the motivation for the inception module, these inception blocks. We have the input here from the previous layer. This can be a stack of feature maps. So one feature map would be one channel here on the input, or it can be the original image. If it's a color image, it will be a stack of 3 matrices with red, green, and blue, for example, and that would be the input into the inception block. And then we have these one by one convolutions that are looking at combinations of the feature maps, but at the level of the individual pixel. And these can serve to control the number of channels that is going into these other convolutional operations, or that will be concatenated into the final output of the inception module. So this way, if you have, for example, 64 layers here, 54 channels in coming from the previous layer, if you pass them through 16 one-by-one convolutions, then you only have 16 channels going into this 3x3 block. And you can do the same thing here, controlling the number of convolutions here, the number of convolutions here. All of these operations have a stride of 1. So it means that the size of the feature map remains the same, even in the case of max pooling. So typically so far, when we did max pooling, we used the stride of the same size as the pooling window. This means that if you were to do this, a 3x3 max pooling would also reduce the size of the map by 3 on each direction. But if you do max pooling with a stride of 1, and if you use padding, then you get an output that has the same dimensions, but for each pixel you will have the maximum value of that 3x3 window in the input. So this is the idea here. Everything here has a stride of 1. If you have, for example, feature maps here that are 64 by 64 pixels, then everything here will produce feature maps of 64 by 64, and they are all stacked together at the end. So this concatenation is a stack of all the feature maps produced by these operations. So the dimension remains the same, and we are just stacking the feature maps, and we can decide how many feature maps come from this operation, one-by-one convolutions, which is just computing linear combinations of these feature maps for every pixel, and then using rectified linear unit for the activation. And then here we do convolutions of 3x3, of 5x5, and again these 1x1 after pooling. So this is these in yellow serve to control the number of channels, basically, so that we can calibrate the number of channels, the number of feature maps that we're going to output here. And this inception model, as you can see, can look at the input data at different resolutions, but it controls the number of channels it's using for each of them, so you can adjust the number of parameters that you're going to need and how powerful overall the module is, while at the same time you're looking at different scales of your input. This was used for GoogleNet by stacking all these inception modules. So you can see here one inception module, another one here. Sometimes they are interspersed with pooling operations. These are actually which tried to reduce the size of the map, but then you can have stacks of inception modules that do not reduce the size of the map here. So all of these wider parts here are the inception modules, and they used the inception modules to create this network. In addition, they also added these intermediate classifiers. So the final classification is done here with the softmax on the 1000 different categories. But they also added classifiers here and here that are branching out of the network at intermediate stages. This also counted a bit, about 1/3, towards the loss function. And the idea here initially was to try to speed up the training of the previous layers, because if you put a classifier here, you are effectively trying to train a network that has only this dimension, and the result of this network will then be used by the following part in order to train this network here, and then the result of that would be used for the final network. So the initial idea was that this could speed up training in the early stages by giving more information to the previous layers in order to organize them. It did not work out exactly like that, but it seems to provide some regularization, so reducing a bit overfitting by adding these intermediate layers. But this is a feature of this architecture that I think is no longer used in more recent ones. So the inception block was one idea of trying to combine different channels in parallel. These intermediate classifiers does not seem to be very useful. But then this was the first version of the inception block. The second version was optimized by, this was a paper in the following year, and they optimized this by replacing convolutions of type n times n, for example, these 5x5 or 3x3, and decomposing them into convolutions, into a stack of 1 times n and another stack of n times 1. So imagine that we have this input here, and we start with a convolution that is 1/3. So it's this line here of 3 cells, and we are scanning over the input. So we produce an output like this, where each value here depends, it's the result of the kernel applied to this window here. And the value in the center would be applied to this window, and so on. So this would be a 1 times 3 convolution. If then we do a 3 times 1, we are going in the other direction, perpendicular. So now we create a convolution from these 3 values, and we have a value here that is close to what we would have applying a 3x3 convolution to the input, instead of doing it into 2 steps, but we need fewer parameters. So for these 2 convolutions, we need 6 parameters, 3 for this one and 3 for this one, instead of the 9 parameters we would need with the 3x3 convolution. So the optimal size for these convolutions here was 7x7, at least empirically, as reported in the paper. So what they did was, instead of having 2 7x7 convolutions stacked here, they have these 4, which would be 1x7, 7x1, then 1x7, then 7x1. And the difference here is between 49 parameters per input channel with a 7x7 convolution, but only 14 parameters when you stack two convolutions of 7 by 1 and 1 by 7. So this reduces a lot the parameters necessary, and you still get the same combination, or you get the combinations of the same inputs in the output. You have fewer parameters, so this is as if we were weight sharing over these dimensions. So weight sharing over the horizontal dimension, and then weight sharing over the vertical dimension to save on the number of free parameters. And this is basically the second version of the inception block, which is the same idea that we saw here, but optimizing these convolutions by splitting them into the two perpendicular directions. Okay, so these are examples of neural networks for image classification, and you see that they follow this general approach. We have stacks of convolutional layers with many convolutional operations, and now these blocks can be more or less sophisticated. They can have convolutions in parallel, they can have residual links and things like that, but they have all these convolution operations, and then we go into the dense part of the network to do the classification. And this is the general approach for image classification. One different problem is image segmentation. While in classification we want to assign labels to the image as a whole, in image segmentation we want to assign labels to pixels, basically. So what we want here would be to, from the input image, we obtain a feature map that will tell us the class where each pixel belongs to. If we have many classes, for example, in this example there were 21 classes for the pixels, we can have 21 feature maps here, and then we can do a softmax pixel by pixel over the 21 channels to determine which class each pixel in the image will belong to. And in this case we have the sofa here in green, the cat here in brown, the dog in purple, and so on. So this would be the idea: from the image obtain this classification. So one first approach, before moving on to the approach, I just want to make this distinction here. There are basically two types of segmentation we can do with the images. Semantic segmentation distinguishes the types of objects. So if we have a photo with people, we know that these pixels belong to people, to persons. But we are not distinguishing between different instances of the type person. Instance segmentation does that. So not only identifies that all of these are persons, but it also distinguishes the different persons in the image. We are not going to cover semantic segmentation. I'm going just to give a brief overview. We are not going to cover instance segmentation. I'm just going to give a brief overview of semantic segmentation. So basically identifying the types of objects without distinguishing instances of the same object. So this first approach to this problem, this fully convolutional network, was motivated by looking at how classification was being done with the convolutional networks, that we have this stack of convolutional layers. We reduce the dimension of the feature map, so we are abstracting from the positional aspects of the different patterns in the image, and we convert this into a large number of filters without retaining that information about the positions, and then we have a classification, for example, the cat there. And we could do this in theory for small patches of the image and scan the image and try to classify each small region of the image so that we could find that the cat is over here, the dog is over here, and so on. But this would require repeating the classification for small patches, and then even in that way it would be hard to have a good resolution at the end, segmenting exactly the region corresponding to the cat and the dog. But what the authors here proposed is that we can think of a dense layer as a convolutional operation applied with a kernel size that has the same dimension as the input. So if you imagine that you have an input of 32 by 32 and you apply a convolution with a kernel of 32 by 32, this is actually a dense layer because you have individual connections to each of the pixels in the input. So what they did was to convolutionalize the classification networks by converting the dense layers into convolution layers, and this resulted into a fully convolutional network that becomes independent of the size of the input image. So if you had a classification network that could take a small patch of the image and determine that this was a cat, you can now convert all these dense layers also into convolution operators, pass the complete image here, and you have in the feature maps on the output all the different classifications of all the different patches in the original image. So this was the basic idea. If we convert into fully convolutional networks, we can process the whole image at once, and the output will depend on the size of the input and be variable depending on what the input image is. This gives us a map to classify the whole image, but it's a very rough map because since we have all these pooling operations, we can have an image that is, say, 200 by 200 pixels at the input, but this may result into feature maps that are only 4 by 4 or 3 by 3 or something like that because we shrunk all the spatial dimensions here with the pooling. And then we are left with a very rough map of the classifications of the regions in the image. So the other thing the authors proposed was to upsample from this rough map at the end, produce feature maps that had the same dimension as the original image, and then do the classification pixel-wise on those feature maps. So basically, this first part of the network can just be taken from a classification network where we convert the dense layers into convolution layers. We use the same transformations here on the input image. We obtain this convolution, these feature maps at the end, which are rough maps of the classification of different regions in the network. And then we train an upsampling layer that will convert this rough map into a more fine map with the pixels of the original image classified. And the way the authors did this was using fractional stride convolution. This, along with transposed convolution, are two ways that were used to do this upsample. So we can see a brief representation here. This is an example of transposed convolution where you have an input x. In this case, it has 5 values, and you want an output that is upsampled. So you have more values in the output. And the way you can do this is, instead of sliding a window over the input and producing one output for each position of the window, like we did with the normal convolution, we can imagine that the window now is here in the vertical. And so the value we get here for y would be 3 times that value plus 1 times that value, or the first weight times that value of our kernel, and the third weight times that value added, and then the same thing here, and so on. And we are actually sliding our kernel as if we were sliding it in the direction of the output, and using these linear combinations for given the same value of the input and multiplying by the different weights to start filling in gradually our output vector. So this is the example of transposed convolution, and it allows us to go from smaller inputs to larger outputs by computing these combinations while we slide the kernel along the output instead of the input. Another way we can do this is this fractional stride convolution, is to move the kernel in fractional steps, or perhaps a better way to imagine this is adding zeros to the input. So these gray squares here are just, we can imagine them as zeros added between the input values, which are the white squares here. And so when we pass the kernel over the input in this way, we can have more values in the output than we had in the input. So these are two techniques for doing convolution, but upsampling our values instead of reducing the number of values, as it can happen with convolution if you have a large stride or if you don't have padding and so on. These are not really the best option. We're going to see a bit more about this when we talk about generative models for images. Actually, a better way of doing this kind of upsampling is just doing a simple upsampling on the input, for example, by interpolation. So filling in vectors interpolated between the neighbors, or using the nearest neighbor, just copying the value. So we get now a larger map for the input, and then apply a simple convolution to that. This avoids some artifacts and some problems with this kind of convolutions, transposed and fractional stride convolutions, and it works better. But this was the approach used in this paper, and the idea here is to do use the convolutional part of the original classifying network, convert the dense layers into convolutional layers, and then do one single step of upsampling with these learned convolutions to obtain the map with the classification for all the pixels. And this was done combining information from different layers. So this is a scheme from the paper where you can build these 21 feature maps at the original pixel resolution by doing upsampling from this layer here, from a previous layer there, at different resolutions. So they were combining these feature maps at different resolutions to produce the final output. But it was still just in one step. So we shrink everything and then one step go up to the original resolution. UNet did this differently, and this one seems to work better. It has this symmetric profile that is similar to an undercomplete autoencoder. We're going to talk about autoencoders next week, but the idea here is that we start with the original resolution of our image, and then we do convolutions and pooling and convolutions and pooling, and we reach a representation that has many more layers, or many more feature maps than we started with, but we have a very low resolution in the spatial dimensions of the original image. And now we start doing upsampling and going back in exactly the same number of steps and gradually decreasing the number of channels we have and increasing the resolution. Now, one difference, this is one difference with respect to this fully convolutional network, because it's now a symmetric encoding and decoding, and not just doing almost all the work here and then only in one step going back to the original resolution. Another difference is that UNet uses these skip layers, where in this decoder part, where we are increasing the resolution, we are also receiving as input a copy of the feature maps that were produced in this downward path here. So when we are at this stage, for example, we are getting as input the output of these convolutions here after upsampling, and combining that with the feature maps that were produced at this part of the network. So it's going like this over the U, but it also has these connections that skip the intermediate stages. Another difference is that the upsampling here is done by nearest neighbor or interpolation, so a first step of simple upsampling, and then using a 2x2 convolution with a stride of 1. So you can imagine, if we go back to this diagram, we could simply start with we start with this x so with only 5 values, but then we increase the size of the vector by some sort of interpolation or nearest neighbor copying. So we can copy the nearest value into these missing locations and thus increase the size of the vector. And now if we apply a convolution with the stride of 1, we produce an output that has the same size as this expanded input. But since we are in this case doing an upsample to increase the resolution 2 times in each direction, if we do that, for example, with the nearest neighbor or interpolation, we will get something that is a bit out of focus because we are just copying values. But then when we apply a 2x2 convolution, we can learn how to bring that layer back into focus. So we learn how to improve the upsampling in this way. And this results in fewer parameters compared to some if you use larger kernels for transposed convolution, but also avoids those kinds of artifacts that we're going to see later. So basically, this would be the simplest way of doing upsample. You just use interpolation or nearest neighbor to increase the size of the feature map, and then you apply a 2x2 convolution to the whole thing, and you learn how to bring it back into focus. There were also some differences in the loss function. So you can imagine that when we are doing this kind of segmentation, so if we want to classify each pixel according to the class, we can simply do a softmax activation on the pixels. So each pixel will have its own softmax result and use that for classification. So we can use softmax cross entropy, for example, in this case. If you only have 2 classes, then here would be only one feature map. It's either class 0 or class 1. In that case, you can have sigmoid activation and use the cross entropy corresponding to the sigmoid activation, so the binary cross entropy in this case. This is what UNet used too, so the softmax activation for classifying all the pixels, but it also modified a bit the loss function to optimize the identification of the frontiers between the different regions. So in the learning, in the training set, they identified the boundaries of all the regions in the training images and added a greater weight to those pixels. So they were trying to force the network to minimize the errors done near the frontier of the different regions. But in any case, the basic function would be as if we were classifying each individual pixel, so we can use the same kind of activations and loss functions for these problems. Okay, so to sum up, we saw several different architectures for convolutional networks. This is just a sample of what you have available, but it's to give you this idea that neural networks are very versatile. We can create lots of different architectures, and there are some problems here with trying to solve more complex problems just by increasing the complexity of the network. Because when we do that, when we have more layers, more parameters, and so on, it makes it harder to train the network. And so we can use these different techniques to try to minimize the number of parameters, to try to maximize the flow of information along the network, and so on. So look, in this case of UNet, we have these skip connections here that are giving each of these parts of the network information not only on all the transformations that were done previously, but also skipping right to the initial steps there. So these kinds of techniques can help train the networks. For further reading about this subject, I would recommend taking a look at the different papers. You have the references in the lecture notes. You don't need to study them in detail. The level of detail that you need for the course is this one that I covered in the slides. But if you are interested in these different architectures, then the papers give you a good insight into the reasoning behind these different approaches. Even though some of the papers are already outdated, and there are better networks nowadays, but it's a good idea to look at how the authors reasoned about these different problems, because that is really an important thing, not just memorizing different architectures or tricks, but getting a better understanding of how you can use these deep neural networks and take advantage of the versatility of these architectures. Okay, so let's take a short break and we continue at 10 for the second lecture. See you soon.